Hi, in this lesson we're going to have a look at using scale factor to work out unknown dimensions in shapes. So we've talked in the first video about the idea of enlargement and reduction and about how shapes are similar if they've got the same scale factor. So let's just recap on a couple of points here on the screen. That shapes are called similar if they're not necessarily identical in size, but one is an enlargement of the other, and that is they kind of look the same. One looks like a bigger version of the other. And similar shapes have two key properties. We talked about the second one in the first video, which was each pair of corresponding sides has the same scale factor. Corresponding means matching, for instance, the lengths, the two lengths of the shape, or the two heights, the ones that are the same, that represent the same dimension in each one. The first one isn't so important in rectangles and squares and the likes because all the angles are right angles, but it's really important in triangles. You've got to make sure that that the matching angles are equal. Okay, so in other words, a similar shape has the angles in each of the relevant places are the same. So for instance, in these two triangles up at the top, what we could say is, of course, that the matching angle, I would say that this one to the right hand side on the left here matches up with this one here. And in similar shapes, these two would be the same size. Similarly, it looks like a right angle, so I assume that they are. That would be the same. And then this triangle at the top, in each case, would be the same. So I would call them kind of matching angles or in the shapes. They would have to be exactly the same size in order for the shape to be similar. Okay, and we finished off the lesson last time by looking at being able to just quickly look at shapes and work out unknown sides. So in this case here, we've got two similar shapes. And if the length here is 8 and the length here is 24, what we can do is work out the scale factor. And we can work out, we're basically saying, what do we multiply by 8 to get the answer 24? Because they're the kind of matching sides. The answer to that would be 3. So that's the scale factor, is 3. And yep, that's right, it's bigger than 1, and that's why the shape is an enlargement of the other one. In order to work out the height of this triangle here, all I would do is apply the same scale factor because I know that they're similar shapes. And we can say that 5 times 3 is 15 centimeters, so I can be confident that this dimension here is 15 centimeters. So we're going to formalize it a little bit because it's good not just to do things in our heads but to write stuff down. So let's have a look at this example. These shapes are similar now. That's a really important phrase that you're going to need to be sure of. In all of these questions, there must be a statement to say that the shapes are similar, otherwise we can't use this technique at all. Okay? So these shapes are similar. Calculate the value of x. What's the height of that larger triangle? Okay, so the first thing we're going to have to do is to work out what the scale factor is. Okay, so we write down here. Now, it's always a good thing as well to think, is it an enlargement or is it a reduction? Okay, so here we've got x is the new shape. Always think about x as the new shape that we've got, which means that it's it's an enlargement. So we can actually write down enlargement scale factor. Okay, now scale factor, we can think of, okay, so matching sides are 5 and 20. So I did say before, all we're trying to do is to think 5 times what gives us 20. And in this case, it's quite straightforward if you know your multiplication tables. 5 fours are 20. What about if it's not a straightforward multiple of the other? Well, if you think about what we're doing is we're taking 5 and we're dividing it into 20. How many times did 20 go into 5? So in other words, we're actually making it as a fraction. What I'd like to see you do is write the scale factor as a fraction. So you take the new value, divide it by the original value. Another way of thinking about it is if you've written down the word enlargement, the big number goes on top. Okay. Another way of thinking about it is if you want to make an enlargement scale factor, you need to make a number that's greater than 1. And you do that by, from the two numbers in your fraction, making it an improper or top-heavy fraction. So there's various ways to try and get that fraction right. In this case, 20 divided by 5 is 4, so our scale factor is 4. What we can then do is to say that the value x that we're trying to work out is going to be the matching value on the original shape, which is 3 centimeters, multiplied by the scale factor. So therefore x is 3 times 4, x is 12 centimeters. Now in this case we could have done that a little less formally. I've put in a number of bits of working, but it's a good story to tell, and that's just because you can work something out in your head doesn't mean it's not worth telling the story. We've shown how we've worked out the enlargement scale factor. We've then stated that the unknown side is the matching side multiplied by that scale factor. I've substituted in 4 for the scale factor and then worked it out. Okay, let's try another one. These shapes are similar, so we've got that confidence that we can use this technique, calculate the value of y, the length of y. So we've got two triangles here. We're told they're similar, and if you look at it, they look as though they're the right way up. In that case, triangles can be shifted around or they can be rotated, but if you notice that this triangle has an obtuse angle at the bottom left, and so does this one, so it looks as though they've been orientated the correct way, and that's important because it means that we're going to match 9.6 with 16. Now that's the only matching pair that we've got. You notice we don't have the side that goes with 8.4. We don't know obviously what y is. So we're looking for a matching pair. We've got 9.6 and we've got 16. So we can say, now look at where y is. Y is on the small shape. So we're actually looking for a reduction scale factor, which is going to be a number less than 1. So we can write down the word reduction. Scale factor equals. Now we're writing the word reduction scale factor because we're looking for a number that's less than 1. So we've got 9.6 and we've got the number 16. How do we make a fraction that's less than 1? Well, in this case, what we do is we put the small number on the top. That makes a number less than 1. Another way of thinking it is the reduction scale factor, to make it smaller, has a small number on top. Okay? Now in that case here, 9.6 divided by 16, we could use a calculator. There might be other ways. Sometimes you have to do this without a calculator. It might be an assessment where there isn't a calculator that you're allowed to use. So there are various strategies that you could use. For instance, in order to simplify this without a calculator, I can multiply both the top and bottom by 10. And that would give me 96 over 160. And then I could go ahead and try and find some common factors. For instance, they're both even. They're also both in the 8 times table, I notice. So I'm just going to jump to that. Divide through by 8. That would give me 12 over 20. They're both even, so that's 6 over 10 and 3/5. Okay, so I could use 3/5 as my scale factor, or 0.6. Because of the decimal values here, I'm going to kind of assume that I'm going to just change it to a decimal fraction here. So you don't have to use the simplifying fraction techniques. Just you can if you need to, that's all. So we've got a scale factor of 0.6 or 3/5, and that's consistent with the fact that it needed to be less than 1. I'm actually trying to work out then the value of y. So we can write down y equals, there's y. So our matching side is 10 centimeters. So we can say that y is going to be that 10 centimeters multiplied by our scale factor. I can put the numbers in. So that's 10 multiplied by 3/5 or 0.6. In this case here then, y is going to be 6 centimeters. Okay, so using the scale factor, a couple of other examples, which then is not about calculating sides but determining. It says determine if these triangles are similar. Okay, so what are the rules? The rules are that all the scale factors are the same. In other words, if we find the scale factor of each of the three sides, they need to be the same number. Otherwise, it's not they're not similar. Okay. Now the other problem with this is that you notice the triangles are not kind of aligned correctly, and just like the last one, we can get a wee hint in that we've actually got an obtuse angle, an angle bigger than 90 here. But look where the obtuse angle is here. In other words, what I really want to do is to maybe rotate this triangle here until it gets to the same kind of position. Okay, so I'm going to move it. Now, watch, the problem is it's going to have to move the sides as well. So if I rotate this here, do you remember what, look, the 33 was that long side and 25 was at the top, which is now down the left-hand side. Whoa. There we go. So that's there, and that's there. So it takes a wee bit of getting used to, but that's now that's the same diagram, okay? But it's really important that you make sure that the matching sides are indeed matching. The longest sides match up, the shortest sides match up, and then the middle sides match up. So I think I'm good to go here. So what I'm going to do is I'm going to number them, okay? You don't have to, but it's a technique. So I'm going to call this side 1. I'm going to call this side 2. I'm going to call this side 3. So that I can just say side 1, and it helps with the communication of what's going on. Side 1, okay? The scale factor, well, it doesn't really matter as long as you're consistent. Let's go from here to here. Do you notice in actual fact that the shapes are definitely not drawn to scale, because 7 centimeters and 16, clearly the 16 one should be bigger. I'm just going to go with enlargement scale factors. So enlargement scale factor is what I've got. I've got 7 and I've got 16.1. To make it an enlargement scale factor, the big number has to go in the top. 16.1 divided by 7. Well, I'm not going to work that out as a fraction. I'm going to make it a decimal fraction. 16.1 divided by 7 is 2.3. Okay, 2.3. So we don't have anything to compare it to. Let's have a look at side 2. So we're going to use 11 and 25.3. So the enlargement scale factor here is 25.3 divided by 11. And if I do that on my calculator, I've already got a wee hunch that, 2.3. There we go. Good. So we're looking good here. So two similar scale, we've got identical scale factors. So if side 3 has the same scale factor of 2.3, then our triangle is indeed, the triangles are similar. So enlargement scale factor, what are the matching sides here? 13.5 and 33. So again, to make it bigger than 1, I need to make it an improper fraction. 33 divided by 13.5. And I get, 2.444. And I have to round it. Now, what we'll find here is that the side 3 doesn't have the same scale factor as sides 1 and 2. Because of that, the triangles are not similar. Okay? So we can see here that as all scale factors are not the same, the triangles are not similar. Okay, so really important. If we'd got 2.3, we could say as all scale factors are the same, the triangles are similar, but because they're not, we can say they're not similar. Okay, and one last quick observation is that we can actually, without any dimensions, we can determine if triangles, this is a special triangle one because of the angles in it. Well, is that a special triangle one? Not really. I suppose it could be any shape, but we usually do it with triangles here. Are these triangles similar? Well, the rule that we had was that all of the matching angles had to be equal. So we've got a wee bit of an angle fact game going on here. If that's 28 degrees and 73, 28 plus 73 gives us 101, which means that we know that the three angles add up to 180, so that's 79 degrees. With this one here, 73 and 79 are 152, and so this is 28 degrees. Okay, are these triangles the same? Well, if you notice that if we were to rotate one of them, say to rotate that so the 28 degrees is at the top, you could see that the 28 would match with the 73 and the 79. They have the same angles, and therefore the triangles are similar, and we can write as the matching angles are equal, the triangles are similar. Okay, so lots of different wee examples about how we can, first of all, calculate dimensions if we know the shapes are similar, but then a little technique that we've got to check to see if the shapes are similar themselves. Okay, hope that's been helpful. You can practice some of these examples.